Good morning, everyone. Welcome to the next lecture. Today we will discuss about different concepts in matrix like trace of a matrix, singular and non-singular matrix, and rank of a matrix. First, we are going to consider what actually mean by a trace of a matrix. See, trace of a matrix is the sum of diagonal elements in a square matrix, which is generally considered from the upper left to the lower right, and which is generally denoted by trace of A. Consider a generalized matrix A, which is equal to A11, A12 up to A1n, A21, A22 up to A2n, and A11, A12, M2 and up to Amn. See, we know in a matrix A11 is the element which belongs to first row and first column, and A22 which belongs to the second row and the second column, and up to Amn which represent the mth row and nth column. And the same way we can define the other elements also. So it is order Mn and the total number of elements in the given matrix is m into n. So the formula for calculating the trace of a square matrix is the sum of Aii, which is I is starting from 1 to n, which is equal to A11 plus A22 plus Amn. See here, trace of matrix A is equal to, the symbol sum is representing the summation, indicating that we are summing up a series of terms, and I is equal to the index of summation, which is starting from 1 and going up to n. And here Aii, which represent the elements of a matrix A located at the ith row and ith column. So we can calculate the trace of a matrix by adding up the diagonal elements, that is A11, A22, Amn. If you go for adding up all the diagonal elements, then it is generally known as trace of a matrix. Consider one 2 by 2 matrix. See, we have a 2 by 2 matrix is 3, 4, 1, 2. It is a 2 by 2 matrix A. We can find the trace of a given matrix, that is, we are going to sum up the diagonal elements, that is 3 plus 2, which is equal to 5. So the trace of a given matrix is equal to 5. We are just going to sum up the diagonal elements. Similarly, if you are having the another matrix, that is matrix A is equal to 1, 2, minus 3, 2, 0, 4, minus 3, 4, 6. See here, the trace of matrix is nothing but you are just going to add up the elements in the diagonal matrix. So here, see, diagonal elements are here 1, 0, 6. So if just go for adding up 1, 0, 6, then it is equal to 7. So the trace is only defined for a square matrix n by n, and that means we can find the trace of matrix only in a square matrix. So I hope you understood what actually the trace of matrix means. Now we are going to introduce another concept which is known as singular matrix. See, a singular matrix is one whose determinant is 0. The determinant value is equal to 0, then such a type of matrix is generally known as it is a singular matrix. If the determinant of a matrix is equal to 0, it means that there exists a linear dependent relationship between at least two row or columns. Then we are generally saying that there exists a linear dependent relationship between at least two or more columns. Then we can say that there is no unique solution is possible. In this case, there is no unique solution is possible, and given matrix does not have an inverse. The solution can't be found. Thus the matrix is singular if and only if the determinant is equal to 0. As against the singular matrix, we have a non-singular matrix as well. See, a non-singular matrix is one whose determinant is not equal to 0. If the determinant value of a given matrix A is not equal to 0, then such a type of matrix is generally known as it is non-singular matrix. That is, if the determinant of a matrix is not equal to 0, which means that there exists a linearly independent relationship between two rows or columns. We have a linear independent relationship between two rows or columns. Then we can say that there exists a unique solution as well. We can found the unique solution and the given matrix is invertible. That is, we can also find the inverse of a given matrix. And thus, the matrix is non-singular if and only if its determinant is non-zero. Let us consider some examples so that it will be more clear. See, we have a given matrix, that is matrix A is equal to 3, 5, 4, 1, 4, 2, 3, 5, 4. It is a 3 by 3 matrix. Now we are going to find the determinant value of given matrix. We are already discussed how to find the determinant of a given matrix. See, here we have a 3 by 3 matrix. So here I am going to consider the first element, that is 3 into crossing the concerned row and column. Then what is remaining here? 4, 2, 5, 4. We are going to cross multiply. See, we are going to take the product of the diagonal elements, that is 4 into 4 minus 2 into 5. Then we are putting the minus sign here, that is minus 5, going to take the second element, that is 5, crossing the concerned column and the row, then it is 1 into 4 minus 2 into 3. Plus, considering the third element, that is 4 into crossing the concerned row and column, then 1, 4, 3, 5. We are going to multiply the elements in the diagonal line, that is 1 into 5 minus 4 into 3. So if you go for simplifying it, see, it will become 3 into 4 into 4, which is equal to 16, minus 2 into 5, which is equal to 10, minus 5, 1 into 4, which is equal to 4, minus 2 into 3, which is equal to 6, plus 4 into 1 into 5 minus 4 into 3, which is equal to 5 minus 12. So if you multiplying this, then it will become, see, 3 into 16 minus 10, which is equal to 6, minus 5 into 4 minus 6, which is equal to minus 2, plus 4 into 5 minus 12, which is equal to minus 7. If you go for multiplying these terms, then it will become 3 into 6, 18, plus minus 5 into minus 2, which is equal to plus 10, then 4 into minus 7, which is equal to minus 28. So here 18 plus 10, which is equal to 28 minus 28, which is equal to 0. See here, the determinant value is equal to 0. If the determinant value is equal to 0, then the matrix is known as it is a singular matrix and there is no unique solution is exist in the case of a singular matrix. That is, if the determinant value of a given matrix is 0. So here the determinant value is 0. So we can say that it is a singular matrix and there is no unique solution is found. Consider another example. See, matrix A is equal to 1, 4, 2, 3, 5, 4, 2, 3, 2. Now we are going to find out the determinant value here again. Considering the first element, then crossing the concerned row and column, then 5 into 2 minus 3 into 4 minus 4 second element, that is 4 into 3 into 2 minus 4 into 2 plus third element, that is 2 into 3 into 3 minus 5 into 2. If you go for simplifying it, then its determinant value will be come out with 4. So here the determinant is greater than 0, it is not equal to 0. So we can say that the matrix is non-singular and we can find a unique solution for the given matrix. So here the matrix value is equal to 4, which is not equal to 0, it is greater than 0 or it is not equal to 0, and the given matrix A is a non-singular matrix and we can find the solution for this given matrix. Now we are going to consider another concept which is known as rank of a matrix. See, what do you mean by rank of a matrix? See, the rank of a matrix is defined as the maximum number of linearly independent rows and columns in a given matrix. The rank of a matrix, which is generally denoted here, it is row A. We are saying that it is rank A. It is equal to the order of highest order non-singular square matrix. Or you know what actually they mean by a non-singular matrix. A non-singular matrix is a one whose determinant is not equal to 0. So it given contained in a given matrix. So thus the rank of matrix is a simple test for linear dependence, whether the two rows or columns have linearly independent or dependent. We can check by using the rank of a matrix. So the rank of a matrix cannot exceed its rows and columns, whichever is smaller. So the rank of a matrix is always less than or equal to the minimum number of rows and columns. So in the case of a rank of matrix, we can find this maximum number of linearly independent rows and columns in a given matrix. So this particular result, that is rank of matrix, will showing that it is row A and it is showing that maximum number of linearly independent rows and columns. Now let us assume we have a square matrix of order n. Here we have a square matrix of order n. Then if the rank of a square matrix A is equal to the n, the row of A, that is rank of given matrix A is equal to n, which means that the matrix is said to have a full rank. In this case, the matrix A is a non-singular matrix, meaning it has an inverse and its determinant value is non-zero. It is here the fact that the rank is equal to the number of rows or columns, which means that the row and or columns are linearly independent. So if the rank of matrix is equal to n with given that the square matrix of order n, then we can say that it is a full rank. And here the rows and columns are linearly independent. Now consider here, if the rank of a square matrix A is less than order n, because given question, that is the square matrix is having the order n. But if the rank of matrix is less than n, which means that the matrix is said to be a singular matrix, and in this case there is no unique inverse is found and the determinant value is equal to 0. So here the rank is less than the number of rows or columns, which means that there are linear dependency among the rows or columns, resulting a 0 determinant. We will check it by using an example so that it will be more clear. See, consider an example. We have a 2 by 2 matrix, that is matrix A is equal to 4, 6, 4, 7, 9. And we want to find out the rank of a matrix. See, first we are going to find out the determinant value of given matrix and check whether the determinant value is equal to 0 or not. See here, the determinant value of 2 by 2 matrix can be found by taking the product of diagonal elements and subtract it from the product of the off principal diagonal elements. See here, it is 6 into 9 minus 4 into 7. So which is equal to the determinant value 6 into 9, which is equal to 54 minus 4 into 7, which is 28. So the determinant value here, which is equal to 26. Here the determinant value will become 26. So this 26 showing that it is not equal to 0, which means that the rank of matrix is here it is 2. The rank of matrix is here 2 because the determinant value is not equal to 0. The given matrix A is a non-singular matrix and the given matrix, the order is 2 by 2 matrix. That means we have a 2 rows and columns which are linearly independent. So here the rank of matrix is equal to 2. So now we are going to consider another example, that is given matrix A is equal to 4, 6 and 6, 9. See here, we want to find out the determinant value of a given matrix. The determinant of matrix A is equal to 4 into 9 minus 6 into 6. See, 4 into 9 minus 6 into 6, which means that 4 into 9 which is equal to 36 and 6 into 6 which is equal to again 36, and the determinant value is here is equal to 0. Since the determinant value of a given matrix is equal to 0, which means that the matrix is a singular matrix and its rows or columns are linearly dependent. Here the determinant value is equal to 0, so it is a singular matrix and the rows and columns are linearly dependent. And in this case, the rows and columns can be expressed a linear combination of each other. And although we can say that the determinant is equal to 0, which does not indicating that the matrix, it indicating that the matrix is a singular matrix, but it does not mean that the rank of matrix is not necessarily 0. Since it is not a null matrix, we can say that there are some positive elements in a given matrix. So the rank of a given matrix is not 0, it is rank is equal to 1, because we have some positive elements in the given matrix. It is not a null matrix, so we can say that it is 2 rows, but here it is rank of matrix is equal to 1. Now consider the another example. We have a given matrix A is equal to 3, 6, 5, 2, 1, 8, 7, 9, 1. It is a 3 by 3 matrix. First we will check with what is the determinant of this given matrix. See, we can find the determinant of a given matrix that is 3 by 3 by taking the first element, that is 3, into crossing the concerned column and the row. What is remaining here? The sub matrix, that is 1, 8, 9, 1. I am writing here, minus the second element, that is 6, into, then concerned row and column can be cancelled out. What is here remaining? 2, 8, 7, 1. Plus the third element, that is 5, into, crossing the concerned row and column, we have 2, 1, 7, 9. Now we are going to consider the solution for this particular calculation. See here, it is 3 into 1 into 1 minus 8 into 9 minus 6 into 2 into 1 minus 8 into 7 plus 5 into 2 into 9 minus 1 into 7. So if you go for simplifying it, then it will become 3 into 1 into 1 which is equal to 1 minus 8 into 9 which is equal to 72 minus 6 into 2 into 1 which is equal to 2 minus 8 into 7 which is minus 56 plus 5 into 18 minus 1 into 7 which is equal to 7. So here 3 into minus 71 minus 6 into minus 54 plus 5 into 11. Then if you go for simplifying it, then it is determinant value is equal to minus 213 plus 324 plus 55 when it is equal to 166. See here, the determinant value is not equal to 0. We can say that it is a non-singular matrix. It is a non-singular matrix because the determinant is not equal to 0. And here we can say that the 3 rows and columns are linearly independent. This particular amount showing that, the determinant showing that, see here, the 3 columns and rows are linearly independent. Since our determinant value is not equal to 0, then the highest order of this given matrix, that is 3 by 3, that is rank, will become 3 also. Okay, I hope you understood. Now let us consider another example. We have a given matrix B which is equal to 5 minus 9 3, 2 12 minus 4 minus 3 minus 8 and 6. First we will go for finding the determinant value of given matrix B. So it is equal to 5 into crossing the concerned row and column, it is 12 minus 4 minus 18 6, then minus, putting again we have the minus 9 into cutting the rows and columns here, it will become 2 minus 4 minus 3 and 6 plus the third element, that is 3 into 2 12 minus 3 minus 18. So here 5 into 12 into 6 minus 4 into minus 18 plus, because we are 2 minus sign are here, minus into minus, it will become, it is plus 9 into 2 into 6 minus 4 into minus 3 plus 3 into 2 into minus 18 minus 12 into minus 3. If you go for simplifying it, then it is 5 into 12 into 6 which is 72 minus 4 into minus 18, which is equal to minus 72, plus 9 into 12 minus 12, because it is here minus 4 into minus 3, which is plus 12. Again we have a minus sign here, so we are putting it is minus 12, plus 3 into 2 into 18, which is equal to minus 36, plus, because both we have 2 minus sign here, so it is 12 into 3, which is equal to plus 36. If you go for simplifying it, then 5 into 72 minus 72, which is equal to 0, plus 9 into 12 minus 12, which is equal to 0, plus 3 into minus 36 plus 36, which is equal to 0. So if you go for simply multiplying these terms, then the determinant value is equal to 0. So since here the determinant value of given matrix B is equal to 0, we can say that matrix B is a singular matrix. And the 3 rows and columns are not linearly independent here. Since our determinant value is not equal to, it is equal to 0, the 2 rows and columns are not linearly independent. So the rank of given matrix is not equal to 0, not equal to 3. Here the rank of the matrix B is not equal to 3. Then what we want to do? In this case, the rank can also be at most of 2 or maybe less than that. In order to check whether it is true or it is less than 2, see, now we are going to test that it is possible to construct at least one non-zero determinant order. See, for that purpose, we are going to start with a sub-matrix. We are going to form the sub-matrix by considering the left upper corner, that is taking the sub-matrix of 2 by 2 order. So here first sub-matrix, that is 5 minus 9 to 12. Let us check what is the determinant value of this given sub-matrix, that is 5 minus 9 to 12. Similarly, we have another sub-matrix, that is minus 9, 3, 12 minus 4, and we can form different sub-matrix. First we are going to consider here, see, first sub-matrix, which is considering from the upper left corner, that is 5 minus 9, 2 and 12. So I am writing here 5 minus 9, 2 and 12, and let us check what is the determinant value of this given sub-matrix. If it is not equal to 0, then we can say that the rank of a matrix is 2. This value is also come out with 0, then we are going to consider next sub-matrix. Again, that also the determinant value is come out with 0, then we are going to consider next sub-matrix. Let us check this one, that is 5 minus 9 to 12. And we are going to consider what actually the determinant of this particular matrix. So 5 into 12, which is equal to 60, minus 9 into 2, which is equal to minus 18. So 60 minus minus, which will become plus, so it is 60 plus 18, which is equal to 78. So since the sub-matrix not equal to 0, we can say that rank of matrix is equal to 2, because we are able to make a non-zero determinant value here, that is 78. So but in the earlier cases, see, we have a matrix B and the determinant value of matrix B was 0, which means that the rank of matrix B is less than 2, since the determinant value here it is equal to 0, confirming that the matrix B is a singular matrix. So in fact, because the matrix is 0, it means that at least one of the row and column in the given matrix B is linear combination of other rows and columns, leading to the reduction of its rank. So that's why we are considered the sub-matrix here, that is 5 minus 9 to 12, and we found that the determinant value is equal to 78. So since it is not equal to 0, we can say that the given matrix, that is the rank of matrix B is equal to 2. There are only 2 linearly independent rows and columns. So we can interpret in this particular way, that is, there is only 2 linearly independent rows and columns exist in this given matrix B. Consider another example. We have a given matrix A, that is 1, 2, 3, 2, 4, 6, minus 3, minus 6, minus 9. We have a 3 by 3 matrix. First we are going to find out the determinant value of given matrix A. So here it is equal to 1 into crossing the concerned column and the row. Then we have 4, 6, minus 9, minus second element, second column and the first row, then it is 2, 6, minus 3, minus 9, plus the third element, crossing the concerned third column and the first row, it is 2, 4, minus 3, minus 6. We are going to simplify it. So it is 1 into 4 into minus 9, which is equal to minus 36, minus 6 into 6, which is equal to minus 36. So minus minus will become plus here. So it is plus 36. Minus 2 into minus 9, which is equal to minus 18, plus 6 into minus 3, which is equal to minus 18, which is equal to plus 18, plus the third element, that is 3 into 2 into minus 6, which is equal to minus 12, minus 3 into 4, which is equal to minus 12. So minus 12, which will become plus 12. Now here we are going to simplify again, that is 1 into minus 36 plus 36, which is equal to 0, minus 2 into minus 18 plus 18, which is equal to 0, plus 3 into minus 12 plus 12, which is equal to again 0. So the determinant value here, it is equal to 0. We can say that given matrix A is a singular matrix because the determinant value is equal to 0. So matrix A is a singular matrix and the 3 rows and columns are not linearly independent. Hence we can say that the rank of matrix is not equal to 3. It is not equal to 3. Since the determinant value is equal to 0, it is a singular matrix, so the rank is not equal to 3. Then what is next possibility? It can at most be 2. So to see this, now we are going to test that it is possible to construct at least one non-zero determinant order. So for that purpose, we are going to start with a sub-matrix from upper left corner, taking 2 by 2 determinant. See, first sub-matrix here, it is 1, 2, 2, 4. See, I am considering the 1, 2, 2, 4 first sub-matrix 2 by 2 order. So it is going to consider the determinant value here. Then it is 1 into 4, 4 minus 2 into 2, which is equal to minus 4, which is equal to 0. Again, the first submatrix determinant value again come out with 0. Now the next I am going to consider the next submatrix here. See the next submatrix here, that is 2, 3, 4, 6. And we are going to find out the determinant value of 2, 3, 4, 6. See it is 2 into 6, which is 12, minus 3 into 4, which is again come out with 12. So 12 minus 12, which is equal to 0. Then if this is also come out with 0, then we are going to consider another submatrix, that is 2, 4, minus 3, minus 6. So again we are going to find the determinant value here, 2 into minus 6, which is equal to minus 12, minus 4 into minus 3, which is equal to minus 12. So if you go for considering here minus 12, which will become plus 12. So minus 12 plus 12 again, which come out with 0. So again we are going to consider another submatrix from here, that is 4, 6, minus 6, minus 9. See here it is 4, 6, minus 6, minus 9. And we are going to find out the determinant value again here. So here 4 into minus 9, which is equal to minus 36, minus 6 into minus 6, which is equal to minus 36 again. So here minus 36 minus minus will become plus. So minus 36 plus 36, which is equal to 0. So again the determinant is singular. So we can say that again we are going to consider another submatrix, that is 1, 2, 3, 6. 1, 2, 3, 6. This is also another possible submatrix of a given matrix A. And let us check whether the determinant value is equal to 0 or not. 1 into 6, that is 6 minus 3 into 2, which is equal to 6. So 6 minus 6, which is again come out with 0. Then is there another possibility of submatrix? See here 2, 6, minus 3, minus 9. This is also another possible submatrix of 2 by 2 order. And let us consider what is the determinant value here. So it is 2 into minus 9, which is equal to minus 18. Then 6 into minus 3, which is minus 18. So we have minus 18 will become plus 18. So minus 18 plus 18, again it is come out with 0. So all the submatrix of a given matrix A is also a singular matrix. because its determinant value is equal to 0 and all the second order determinants are 0. Hence the rank of matrix again it is not equal to 2. Then what is the next possibility? The rank may be 1. Rank may be 1. Again the matrix is, why it is 1? Because it is not a null matrix. Hence the rank of matrix is here, it is equal to 1. So here all the second order determinants are 0. So the rank of matrix A is not equal to 2. Then the next possibility, that is the rank of matrix is equal to 1. Why it is 1? Because it is not a null matrix. We have many positive elements are here. All the elements are the positive or some of them are negative. So here it is not a null matrix, is a rank of matrix A is equal to 1. So in this way we can find the rank of a given matrix, and let me conclude here. Today we have discussed what actually mean by the trace of a matrix, singular matrix and non-singular matrix, rank of a matrix. I hope it was clear to you. We will see in the next lecture. Thank you.